So in this video, we're going to be going over the shortened Unix path problem. So we're going to be given a valid Unix path that may not be the shortest possible Unix path, and we're going to have to translate it to the shortest possible Unix path from that. So really quickly, Unix is a family of operating systems. It's not any one particular operating system, but it's most notably Mac OS and Linux are both flavors or forms of Unix. And then a Unix path is a string representation of the location of a file or a directory in a Unix file system. To illustrate this, we have an example file system. So you can see at the top, we have this root directory or slash. The way that Unix represents the parent of all parents is known as the root, and that's just this slash. Next, you can see that we have three subdirectories. So there's foo, bar, and baz. And you can see inside of foo, there are two other nested directories in it. And you can see to the right of them is the valid Unix path representing where they are. So the root is just represented by this single slash. The foo directory is just represented by slash foo. Bar, you go from the root to foo to bar. So root, foo, bar. And for baz, it's the same thing. You go from root to foo to bar to baz. Going out to reference bar and baz, you go to the root to bar and then root to baz. However, not all file systems are represented from the root, and those actually are known as absolute paths, but sometimes we're going to be given relative paths. There are two things you need to know to represent relative paths, and they are the single dot, so this denotes that you want to go to the current directory, and the double dot, and that represents that you want to go to the parent of the current directory that you're in. So to illustrate this, let's say that the root foo bar is our present working directory. That means if we want to reference, say, the root as a relative path, we could represent it with a slash, which would be absolute, but we want to go to the parent of the present working directory. And using this notation that we learned up here, we can do that by two double dots. So this is the parent, and this is the parent of the parent. What if we want to reference bar itself? Well, using this notation, we can use the single dot, which represents the current working directory. If we want to go one lower, if we want to go to baz, we want to go from the current working directory into baz. And lastly, what if we wanted to do bar or baz, which are outside of it? It's in somewhere inside of the parent. Well, then we'd have to go back twice. So we go foo to the root, and then into bar. Let's say we're doing bar, which is just the one double dot, two double dots, so two jumps, and then into bar. With all of that being said, let's go into a quick example just to check your understanding. So with the same file system that we had in our example, and we are given this path, so this is slash baz slash dot dot slash foo, is there a shorter way to express this? And I'll let you pause for a second if you want to go ahead and do this on your own. Let's just walk through the path. So we start at the root, and then we go to baz. And then after baz, we go back up to the parent. So now we're back at root, and then we go into the foo directory. So at the end of this, we land here in foo. So how do we express foo? That is just going to be the root directory slash foo. So before we start moving into a solution, let's just talk about a couple more rules. So the first rule is that the parent directory of the root directory is the root directory. So what does that mean? If we have a path that looks like this, so we're at the root and then we want to go to the parent of the parent, well, the parent of the root is itself. So you kind of just do this cycle where it references itself. So this is going to resolve into just being the root directory. So on to number two, any path that does not start with slash is considered a relative path. So we talked about relative and absolute paths above, but if you have a Unix path that looks like, say, foo slash bar, but there's no slash at the start, you're going to assume that you're starting in the present working directory, and then everything is from there. And lastly, rule number three, if you go to the parent of a relative path from a relative path, you can chain them. So it's a little bit of a mouthful, but you're going to see this rule illustrated in the examples we're about to go over in this next slide. So here are a couple edge case examples, and I'm going to go ahead and walk you through them. So the first is we're starting at the root directory, foo dot dot slash dot dot. So what we can do is we can cancel this out because the parent of foo is just the root directory. And then we're trying to get from the parent of the root directory. And we know from rule one that that is simply just the root directory. And this next example right after it is the same thing, because this is what was just above. So this is the root directory, and we're trying to get the parent of that. So that is also just slash. or the root directory. Now let's check out this one. So we're at the root directory. This is an absolute path. We're going to go to foo. We're going to go into dot. And we have to remember that above the dot symbol is just the current directory into bar. So if you are in a path and you want to go to the dot directory, that means you're just going to stay right where you're at. So we can simplify this as simply foo bar because this dot doesn't change anything. Okay, now let's look at some of these relative paths. You can see neither of these start with a slash. So these are relative paths, and let's take a look at them. And this is now going to involve that mysterious rule 3 that we saw before. So foo, and we're going to go to the parent of foo. So remember, you kind of have to add like an imaginary slash or a dot slash in front of this. So if we're just going to the parent of foo, that is the current directory. So that's dot. Let's take a look at this. So this is the same as we had above. So we're in the current directory. We can kind of mentally cross this out. And then we're going to the parent directory of that. So using rule 3, if we have a relative path and we're trying to go to the parent of that, you have to chain it. So in our case, chaining looks like this, which can be expressed more simply as this. Because if you don't have a slash at it, you remember you put like an imaginary dot slash in the beginning. So this is how we simplify these relative paths. All right, now let's start working towards our solution. And when we see a problem like this, we want to think in our head right away, is there any data structure that can kind of make my life easier in solving this problem? So I'm going to go ahead and let's just try and simplify this path without using any data structure, and we'll kind of see if any insights pop up, which will lead us in a direction to go. We start with the root directory because this is an absolute path, and then we go to foo. We can see there's a parent directory. So the parent directory we can see is coming right after foo, so we can cross kind of both of these out. And now we're sort of working with this path. We've kind of simplified the front. So now we're at bar, baz, dot, dot. Great. So there's bar, no problem with that. There's baz, no problem with that. And now we see another dot, dot. And what we can do here is we can just eliminate baz. And this leaves us with simply bar. Okay, let's go through another example, but this time with a relative path. So this is a relative path because it does not start with a slash. And we start by trying to go to the parent directory. And we see that there's nothing before it. So we can't really do anything about this. Next, we're going to go to foo, and we can see that we're just going to add that to the right. And we have another parent directory. And this time, there's no special symbol before this. And we'll consider special symbols being the current directory and the parent directory. But because there's a normal path right before it, we can eliminate this. Okay, so now we're working with this dot, dot, slash, dot, dot. And here's another move into a parent directory. And because this is a relative path before it, rule 3, remember, we cannot do anything about this. So this is our final shortened path, is the parent directory of the parent directory. So if you've noticed something from going through those examples, it's that when we come into a special character, which is either the current directory or moving to the parent directory, that solely relies on what we just did before it. So when we were looking at this move to a parent directory, the only thing that we were looking at was foo, whether or not foo was a special character or not. And when we were here, we didn't care that slash foo slash dot dot slash bar was before it. We just looked at baz and we knew that we could eliminate it, right? And when you come into a problem like that, you immediately want to start thinking about maybe this is a problem I can use a stack with. So let's try adding a stack into our solution. So the first thing we're going to do is we're going to tokenize the path. And that's just a fancy word for saying let's split the path into strings. So let's get our tokens here. Great. And I'm going to make a stack here. And what we're going to do is we're going to have two rules. The first is if the token that we receive is a non-special character, all we have to do is simply push it onto the stack. And then when we are pushing onto a special character, so that's either going to be the dot or the dot dot, we have to check, is the element on the stack that we're peeking, is that a special character? And if it's not, so that would be, like foo or bar or baz, we can just simply eliminate it and move on to the next token. So let's do this in practice. So our first token is going to be foo, and we can see that we can simply just push that onto the stack. Next, we have dot dot. So the dot dot, we're going to go through our rules. Do we see, is there a special character which when we peek the stack? There's not, it's foo. So we can just eliminate foo from our stack. So bar, we are going to push that onto the stack. Baz, we are going to push that onto the stack. And now we encounter another dot dot. We can see that when we peek, we see baz. And we are going to pop that off of the stack. Now we've gone through all of our tokens, and the only thing that remains in our stack is baz. So our solution is simply slash baz. Okay, let's try the same stack approach as we used before, but now we're going to deal with a relative path. You can see that this is a relative path because it does not start with a slash. So we're going to use the same approach. First, let's tokenize. Let's put our stack here, and let's start trying to push and pop. So we're starting with our first token right here, which is a ... So we cannot eliminate anything because the stack is empty. So we're simply going to push it. Okay. Next, we're dealing with foo. So foo, we are simply just going to push that onto the stack. Anytime that we have a non-special character, just push it. Now we have another move to a parent directory. We can see that when we peek the stack, there is a non-special character, foo. So we're going to eliminate that. And lastly, we have another ... This time when we peek, we see it is a move to a parent directory, which is a special character. So all we can do is push. Now we're done. We have no more tokens inside of our list. We can see that we're left with 2 ... So our result is going to be, this is a relative path, so we're not going to start with a slash. It's going to be ... .. Okay, so we've gone through an example of solving this problem with a stack using an absolute and a relative directory. So now let's start moving into our solution.
If you're enjoying this video, we have plenty more awesome data structure algorithm and system design explanations on interviewpen.com. You can ask us any questions you have about any kind of topics surrounding data structures and algorithms and system design. We release 2 to 4 videos a week. You can run your code. You can talk to a personalized AI teaching assistant. And yeah, the site's pretty great. Anyway, enjoy the video.
The first thing we're going to do is maintain a flag of whether or not this is a relative directory. And this can be done simply by checking if the path starts at the root directory, which is the slash symbol. Next, we're going to tokenize our input. And finally, we're going to initialize the stack. Now, the meat of the problem is happening inside of this for loop. So inside of the for loop, the first thing we do is check if the token is ... or a move to a parent directory. Then we're going to check the conditions on which we can pop from the stack. And those conditions are, we have to have a non-empty stack and the last element of the stack is not also a parent directory. So if that's the case, then we can just pop from the stack and then move on. So this would be, there is a non-empty stack and we have an element like foo, bar, or baz inside of it when we encounter this move to the parent directory. And as we've seen for the examples above, what we do in that case is we remove it. Otherwise, we're going to check if this is a relative directory. And if that's the case, one of the two things is true. Either we have an empty stack. So let's consider this case. If the stack is empty and we encounter a ... so move to a parent directory, well, we just want the stack to simply be ... the parent directory itself. Otherwise, the stack is not empty, so there exists something on the stack, but the last element on the stack is a parent directory. And in that case, we apply rule 3 and we chain those together. So we'd want to append that to the stack anyways. If we reach the end of both of these conditionals, then we know the following is true. We are using an absolute directory and the stack is empty. But you might be asking, what about this case? What about the last token is the parent directory itself? Well, that actually can't be true because you'll see the only time that we append a parent directory to the stack is if we're dealing with a relative directory. So if we exit from both of these conditionals, we know that the stack is empty and we're using an absolute directory. And in that case, we have to remember that the parent of the root is the root. So what we're trying to do is get to the parent of the root. And so we're going to do nothing because we just want that to be the root. Okay, that was the hard part. Let's finish this up. Now we have this elif token is equal to ... So remember, that's a move to the current directory. And in that case, we can just ignore it. And lastly, if we are not encountered with a special tokens, that means we've taken care of the ... and the single ... Let's just simply add the token to the stack. The last few lines of the solution is simply just formatting our output. So there are 2 cases we have to handle mostly. One, what if the stack is empty? So if the stack is empty, we simply want to return a single ... if we're dealing with a relative directory. Otherwise, we just return the root directory, which is a slash. Then, if this is a relative directory, we just want to join the stack together with slashes. And if this is an absolute directory, we want to make sure that this is prefixed with a slash. So we use this syntax where we append an empty string to the front of what we have in the stack. And in that case, it's actually going to append a slash to the front of joining everything together. And that is our solution. Now that we understand the solution, let's talk about some runtime and space complexity. Before getting into it, let's define 2 variables. We're going to say n is equal to the length of the path string. And we're going to say m is equal to the number of tokens in the path. One thing to note is that m has to be strictly less than n. And that is because it's not possible to have more tokens in the path than we do characters in the path string itself. So let's start looking at this and trying to find out what the runtime complexity is in terms of n and m. So first, let's look at this line right here. which is tokens is equal to path.strip.split. So what this is doing under the hood in Python is it's looking through every character in the path string and trying to split it based on that character. So this line right here is going to run in O of n time. This is dependent on the length of the path string we've been provided. So right off the bat, we know this is at least an O of n solution. Next, let's look at this for loop. So the for loop is going to have O of m iterations, and each of the bodies is going to be a constant time operation because we're going to assume that we can do the pop and append in constant time. So what we have is a O of n tokenization and an O of m loop. And when you add O of n plus O of m, because we know that n is strictly greater than n, that's just O of n. Now let's talk about space complexity. So to do space complexity, let's consider the worst case. And the worst case for space complexity would be that the stack gets completely filled by the number of tokens in the path. Let's walk through an example. If we were given the absolute path root foo bar baz, if we were going through our solution, we're not going to encounter any of the special characters, which means all we do is append to the stack. And that means by the end of the program, the stack would be filled with every token inside of our tokens, which means that the length of the stack is going to be upper bounded by the number of tokens in path. Otherwise, O of m space complexity.
If you enjoyed this video, you can find more content like this on interviewpen.com. We have tons of more in-depth system design and data structures and algorithms content for any skill level, along with a full coding environment and an AI teaching assistant. You can also join our Discord, where we're always available to answer any questions you might have. If you or a friend wants to master the fundamentals of software engineering, check us out at interviewpen.com.